is for you today. It feels very much like a London AI meetup because we've got Selden, Tractable and Datatonic in the same room. Hands up if any of you are familiar with those businesses. Yeah, good. I think we're beginning to see that some of these UK startups are beginning to resonate. I'm particularly pleased actually that Datatonic has spoken in this session for us in the past as well. So I'm very pleased that we've got them coming back to entertain us again. But first of all, we have Marcel and Laurent who join us from Tractable. Tractable doing some really interesting things in the kind of visual AI space. I was lucky enough to hear from their founder about 2 years ago and got very excited about what they were doing, particularly within the insurance space. So if I invite the chaps to the stage.
So yeah, we're both from Tractable, Marcel, Laurent. And I'm a deep learning researcher.
And I'm a senior deep learning engineer.
Yes, and so we thought we're both going to talk something about what we do at Tractable. I'm going to start about essentially how we train models and we do there. And Laurent is going to talk more about how they're going to be deployed.
Yes.
And probably is going to get very much interest by the guys from Selden who's going to tell us what we're all doing wrong.
Yeah, exactly.
Cool. So, Tractable, yes. Thanks for the nice introduction. Who are we? Our broader mission is we want to bring AI to the real world and bring particular progress that has happened on deep learning using images. Bring that to applications that bring real value for practical applications. We have in the history of Tractable, which is not that long, but at least I think 3 years now, is that correct? 3 years. There has been, we've started various projects. But the main thing that we're working on now is the motor insurance industry. So it's the problem of when someone has a car, or let's say someone is driving a car, which can even be a rental car, and they run into some sort of accident, some sort of collision. In many cases, an insurance company will cover at least part of the loss. And so what happens is the car is damaged. It will be repaired by a body shop, but the body shop gets paid by the insurance company, so there's an incentive for the body shop to just overcharge the insurance company because there's no direct there has to be some cost control there. And so how that's implemented is there's sometimes it's an independent party. Sometimes it's a body shop that makes an estimate of how much it's going to cost to repair this car, and then the insurance company is going to say, yes, okay, that sounds reasonable, we're going to do it. And we want to make this whole process more efficient, because this currently the process of creating this estimate is a manual process that requires human experts that take a look at the car, or more, and what's also becoming more common is that human experts looks at photos of the damage. Because if the human expert have to look at the car itself, they have to first of all go to the car, or the car has to come to the expert, which in itself, depending on where it is, maybe it's simple in London, but if somewhere in the countryside can take a while as well. So that just then first of all you have to make the estimate, then the insurance company has to say yes, that sounds reasonable. They have to check it, and only then the body shop can start to repair your car. So there's quite a bit of delay and quite a bit of cost involved in this whole thing. And we strongly believe that, and we just want evidence that we can use the progress that has happened with deep learning, the AI, to make this whole process a lot better. So instead of having this guy here just waiting for this thing to happen, the claim, and having the final estimate, we hope we can make this with AI, and it's all going to be instantaneous and accurate and so on. So what we have to do to make this happen, we have as an input, we have some sort of information about the car, a set of pictures that show the condition of the car, the damaged parts, the parts that are not damaged, just the overall condition. And from that we have to generate an estimate that shows which parts of the car are damaged, what has to be done to it, what has to be repaired, what has to be, the paint has to be renewed, maybe there's some corrosion protection that has to be applied. Then there are all the details about which particular part even behind that might be damaged and so on. And so in order to do this whole thing, to make a final list of things of steps that need to be taken and define a cost figure, there are some other things that we have to do at Tractable to build a machine learning model that is able to do all this. So we have to recognize which parts are even in which image to know what are we looking at. We have to assess which parts are damaged. And we have to predict how severe is the damage, what operations need to be taken. One very simple thing is always, is this part so damaged that we have to replace it? We have to order a new one? Or is it only lightly damaged and we can just maybe just knock out the dent and then it's fine again? So we have to do that, and then we have to map that to, let's say we have to decide, oh, this part is so damaged, we need a new one. We have to also figure out what is the precise part number and how expensive is it, which also is not an easy task. So the first part here are visual models. So these are deep learning visual models that it's a visual problem to assess the damage of the car. The last part is more metadata, is more sometimes a data science question of figuring out, okay, if this is a BMW 2008 and we're looking at the bonnet, how expensive is it? And that's sort of a separate database of a question, which we're not going to talk about that much today. So today we're focusing on the visual part. And one thing that is, first of all, very important is to see if we have an image. Typically, if we look at one insurance claim, so one accident, we will typically receive between 15 and 50 images of the car, some of which will show the whole, let's say, the overall condition of the car, some of which show highlight the damage that has happened to the car, and some of it will also be mostly irrelevant for us, at least will be irrelevant in terms of how irrelevant to assess the damage. There will be images of, let's say, the mileage counter, which are interesting, which maybe are again interesting to see how much value does this car have, is it a total loss, but they are not necessary to say, oh, or not even helpful to say, is this bonnet damaged? So that's why the first thing that we need is something that even classifies the images or sort of categorizes the images into which of all the images that we have belong to a particular part. And then we have to assess the damage. This is shown in this demo UI here, where it's still a fairly simple way where the images, there's a bunch of images that are uploaded on the side here, and then they're automatically categorized to be, in this case, belonging to the front and left fender, to the headlamp, and so on. And then we can make a prediction of, oh, this is replaced and repaired. This is like roughly what we're getting at. Although in detail it becomes more complicated because sometimes we don't have to look at, oh, this is the headlamp, but then there might be even something like, oh, do we have to replace the mounting thing for the headlamp or something like that. But we forget about it for now, and we just make it nice and simple, that we have some big parts that we can assess. And so, yeah, our task, the task that we faced it with as the deep learning research team at Tractable is to build models that are trustworthy and that can be deployed at scale for this problem of, okay, we have a damaged car, someone takes pictures of it, and then make a final estimate on it. And for what we have for this to build such a model is we have a lot of data from partners in the insurance industry that we have partnered with, and they have given us a lot of historical data. So we have loads of images now. Roughly 130 million that are actually showing parts of the car, and where we have a lot of information about like which parts are damaged in this car and so on. And so we have to somehow leverage these 130 million images to train a model that is able to predict all the damaged parts. One typical, I would like to focus. First of all, how do we roughly do this training on this number of images, which we're still growing a lot, so we're still collecting a lot more data every month. So how do we at Tractable train our models? So first of all, the images themselves are stored on Amazon S3, so which enables us to have essentially unlimited storage, and also the bandwidth with which we can stream them, the images for training, is essentially unlimited. Which is very helpful when you compare to any disk. And Then on the other side here, we're using Keras on top of TensorFlow to develop our models and to prototype very quickly. Keras is very helpful for that, probably most of you know. And what we need in between is we need some layer that transfers the images very quickly from this Amazon S3 storage to the training setup on Keras and TensorFlow, which is, as most people do, is using GPUs to accelerate the training. Typically, we use a couple dozen GPUs at the same time. So we have right now roughly many people many researchers at Tractable that run different experiments, and they all have like multi-GPU setups. So there's a lot of throughput that's going through this whole thing. And so we have a data API that downloads these images in parallel, buffers them up, and then decompresses them in parallel on multiple CPU cores, and then delivers them to the training stuff very quickly, which is very useful and very stable at this point. It allows us to train on these very large data sets very efficiently. And this is the basis which we can use in the research team to prototype and to build our models. And so I'd like to focus now on the next 3 slides before I hand over to Laurent on one particular problem that we typically face in the research team at Tractable, and which we believe we haven't really solved yet. And so I'm explaining the problem. I'm showing how we're using TensorFlow to iterate on it. But I'm also very curious whether anyone here has a better idea and who has a solution for us to come up with a better way to solve this problem. Because I still feel how we currently do this is a bit stupid. But maybe, let's see. So typically what happens is we have one car that has been damaged in an accident. There will be multiple, so we have one car, and let's say, just to make it simple, for now we're only interested in one part. So right now, we only want to know whether the front left wing, so that's the piece of metal that is above the front wheel of the car, whether this is damaged or not, and whether it needs to be replaced or whether it can be repaired. That's the only thing we want to do. So we have one car, one accident, one part of the car, we want to know what do we have to do on this. Is it undamaged? Can we repair it? Or does it need to be replaced? And so that means we typically have still multiple images that have been taken of this one part. And we have somehow have to reason over all of them to make a decision. So you can see in this example here, so the front left wing is this part here, the car, so it's above the wheel. And in this image, so it's visible here you can see more the front end of it. So this would be the front light sits somewhere here, if it would be one image. And this is a little bit zoomed out version of this. So what can be seen is that in this image, the front left wing here seems undamaged. So it's at least, I can't see any damage here, so it seems we are fine. There's no visible dent. When we look here, we can definitely see that this is completely dented, and probably, it's not even dented, it's just completely, the metal is wriggled and doesn't look good anymore. So we probably can't, this is, from this image, from what I see now also, I mean, I'm a deep learning researcher, but when you work on this problem, you also have to acquire a lot of detailed industry knowledge about this. So this is a replace, I can tell from this. So we also have a lot of motor engineers working at Tractable that can help us debug the AI, like why was the wrong decision or the right decision. So in this case it's replaced. From this one here, it's again a little bit hard to say what this even is. There is only part of the front left wing visible. Sometimes it's very important here, for example, to see what the gap is to the next part. If there's a large gap, then it probably means that the whole part is somewhat completely bended and needs to be replaced as well. Sorry? Faster. Okay. Faster, okay. Let's go faster. Anyway, so the reason over all of them. And so what we do is, the idea was to take a typical neural network, a deep image architecture, ResNets, and share the weights. So in this case, we just said we restrict ourselves to 4 images. If we have fewer for a claim, we just take insert black zeros there. If we have more, we just take the 4 random ones. And then the question is like, how do we combine them? The idea is from this ResNet, we just chop off the last layers that we are left with the feature vectors, and then there are different ways to pool it. We tried max pooling, mean pooling, concatenate them, and then we come up with a prediction which is not anymore on the image level, but is on the claim level. Which again is important because one of these images, the first one was undamaged, the other two are clearly replaced. So if you just take the average of that, that might be complete bollocks. So yeah, we need to claim the prediction. So faster, we have to. That's why it's so great that we have carrots on top of TensorFlow. We can prototype very fast. We can build this model now very quickly. So we have already this beautiful component here that builds a basic ResNet model. So we can configure how many layers we want to have and so on. We just chop off the last prediction layer here, so we're left with the feature vectors. Here we say, okay, let's do with 4 images per claim, and then we define a new input. We stay here with the typical. This is the typical image dimensions for most deep learning. It's by the ImageNet architectures mostly. It's like 224 pixels width, 224 pixels height, 3 color channels. We insert this additional dimension, which is the number of images that we have per claim, and then we run the same ResNet model that we have defined here with the same weights. We run it on all the 4 images that are in the claim. So we just take 3 different slices out of here and apply the same model, the model that we have here, apply it 4 times to get like 4 different sets of feature vectors for these 4 images. And then we make a combined model out of these by merging them together. In this case, my favorite solution was to concatenate the features and do like that. So we add them all together. And then we do maybe 1 or a couple of fully connected dense layers on top of that. And then again, a prediction. And then we will have, typically for this problem, we have like 5 million or 10 million different historical claims where we have like, oh, we have 4 images and we know the motor expert decision was undamaged, repair, replace, and we can train this. So the short answer is this never worked measurably better than doing the stupid thing of just training everything by image and just looking for each image like, oh, we just separate the whole problem, we forget about that this is 1 car, and we just say, oh, this is 1 image and the decision was replaced, and this is another thing that the decision was replaced on, and then we take the average. Unfortunately, this more complicated end-to-end train thing never worked measurably better than taking the stupid thing. So we're still very open to improvements on how we can do better here. We're very curious to meet smarter people than we are. And in the meantime, we're grateful at least we were able to fail fast with carrots and TensorFlow. And in the meantime, I'm finished now. Laurent is going to show how we can build a working stupid solution, how we can bring that onto production, because it's already pretty good, it turns out.
Yeah. So thanks, Marcel. So yeah, it turns out like this ML solution didn't work, but we still have like a pretty good solution which just analyze like images 1 by 1 and aggregate the results somehow with a pooling layer. And now that we've got this solution, we need to like ship it in production and classify at scale. So here our constraint in terms of like a deployment, we want to do real-time inference. We have a kind of like a very kind of like modest volume of data to ingest on a daily basis. So it's just like 1.2 million per second. So just need like 12.5 image per second throughput. So it's not like I mean, it's nearly something like a CPU can handle. So yeah, so we looked at different and various options on how we can deploy this cost effectively. Because turns out like we have at the moment 1 model per car part. We're covering 12 car parts, meaning there's like 12 part recognition model, 12 damage assessment model, meaning like there's like 24 deep learning model to run at a given time, which kind of like takes a lot of compute. So, okay, so how can we deploy that? So, simple solution, naive approach, take kind of like 1 model, put it into 1 Python process, and put this on a single GPU. I mean, it's nice and good. It's working pretty well. You can get a very kind of like high throughput. Yeah, it's definitely working well when you've got a lot of traffic, but turns out it's quite expensive. It's about like 16K a month because you have to, say here to feed this 3 model, you have to turn on like 3 P2 instances from Amazon, which are quite expensive. And also it's quite wasteful because here we're using 1 GPU per model, but like not of the model are doing inference at the same time. Some are doing more inference than others because, for instance, for the damage models, you only kind of like assess images where the part is present. So how can we do better, and how can we sort of like aggregate this kind of like models somehow to reduce the cost? So 2 options. I mean, like given this sort of like traffic, can we use CPU, or can we find a way to collocate this model onto the same GPU? So CPU turns out it's just like, I mean, not possible. We didn't like dig too much into the detail, but like the current throughput you can get with like a sort of like unoptimized backend, like a TensorFlow backend is 3 images per second. And yeah, I mean, turns out, but like with just like trying to reach the desired throughput with this unoptimized backend would just like literally blow up the cost, and that doesn't even scale. So how can we use GPU, and how can we collocate several models on the same GPU? So, I mean, in terms of pipeline, it's like a pretty standard like pipeline that we have. So we receive a request containing some images, and yeah, so you want to decompress these images, feed them into a classifier, classify these images, and return the results, right? So one thing you can do here is just like, rather than like just running 1 Python process per GPU, you can run several Python processes per GPU. Still pretty naive, but I mean, it's definitely kind of like working better because you can optimize a lot more the GPU usage. But one thing you have to do is constrain the memory usage of your process, because you have to kind of guarantee a certain upper bound, otherwise you're prone to kind of like memory overflow. And yeah, so meaning that that you cannot scale like in terms of like the number of model you can pack onto the same GPU. It doesn't really scale very well, and the reason being is that when you have a Python process running with this kind of like Keras TensorFlow model, is that in the GPU memory you need to have the like a memory reservation for the TensorFlow framework and the Keras framework we use on top of it, which is about 300 megabytes. Then you load the model itself, which is I guess about around like 100 megabytes or something, and then you can reserve some extra memory for your batch. So, I mean, in terms of implementation, the solution is very, very easy to implement. It's like almost no code change. What you just have to do is set up your TensorFlow session to not allow any kind of like memory growth, and just like reserve a fraction of the memory upfront. So here, for instance, if we want to pack 5 models on the same GPU, we just put like, you just reserve 20% of the GPU memory per process. So in terms of like benchmarking, how did it go about this this solution? Here we're on our production system, we're using instances which have a GPU card with 8 gig of RAM, meaning that here on maximum we can fit about 6 processes in parallel. And we can see that like these processes are actually utilizing like 100% of the GPU compute, which is pretty good. I mean, having said that, is there any sort of like kind of like decrease in terms of performance by just like stacking more models onto the same GPU? I mean, yes, obviously there is a drop in performance. 5 minutes? Okay. So yes, there is a drop in performance if you just consider like a single model, but in terms of the overall throughput, it doesn't really change. Like here, if we because we've analyzed the throughput here for when we packed 1 or up to 6 models on the same GPU, and so we ended up with the same throughput. So meaning that like on average, we still got about 160, 170 images per second on the same GPU. okay, I mean, like, turns out here that like we can pack 6 models on the same GPU, so we only need something like 4 cards rather than like 24, which is already a pretty big saving, and can reduce our costs up to like kind of like 3K per month or something, rather than like 16, so it's already good. But like, can we do any better? Turns out, yes, we can. So one of the big things here, which we didn't kind of like optimize, is this image decompression problem, because that's one of the big part of any sort of like deep learning processing pipeline, at least like the pipelines which deal with images. And so if we kind of like share this load, so meaning we take a single Python process which does the image decompression, and we sort of like warm up lots of models on the same process and sequentially kind of like run the model one after another, you can also gain some extra performance boost, in the sense that you don't pay this big overhead more than one time. You pay this overhead once, and then you can pack up as many models as you, as many models as you possibly can, and you just need to leave like a memory space for a single like batch size or something, which is a bit more optimized. So what about the performance of this approach? So in terms of like kind of like model capacity, so we can now fit up to about 85 model on this single card, which is like definitely a lot better, because at least in our problem we care about scaling in terms of like the number of car parts we want to classify. So meaning that we can definitely kind of rapidly grow the number of models we have to deploy until we have Marcel fixing our beautiful MIL model. Yeah, so like we got definitely like a better scalability here. In terms of GPU utilization, there's like a slight drop compared to just packing up more processes, but we're still having like a pretty decent throughput, right? I mean, we're about 75–80% utilization, and in terms of the pure model throughput, we're actually doing even better. So that's pretty good. And yeah, so with this sort of like approach here, we managed to sort of like pack up all of our model on a single card. They all average 7 images per second if they all run kind of like equally at the same time. And it just means we need about 2 GPUs to handle like our sort of like minimum required sort of like traffic. So here with a single box of like 4 GPUs, we achieved redundancy and high availability, and we also have like twice as much throughput as required to handle like every request that comes in on a single day. Yeah. So yeah, that's it. Thanks.
We are a little tight for time, but I think we can accommodate 1 or 2 questions. Does anyone have a question? Yes?
Have you tried the recurrent neural networks that take the different images from the same car as the input of different time steps, and so then you use recurrent to
Yes.
output?
Yes, that's an excellent idea. We have tried that, maybe not with as much depth as we would like to. We had a UCL student last year who has tried that mostly in a simpler setting, and it looked very nice on simpler problems, which were not the current choice problems, but something like, I think we did it on some endless examples, right? Like trying to take multiple images and trying to get the network to learn to add up digits and stuff like that, so that worked very well. But it hasn't, up to now, hasn't yielded improvement on that. But yeah, I agree, it's, I think this makes a lot of sense.
The other thing you can try is to have the same model tell you is it damaged, and also what part it is, so you have multiple outputs.
Oh, yeah.
Yeah. Yeah, we also tried that.
Yeah, I guess we did.
George?
Quick question, capacity. You said your output is 7 images, and you said initially that you were having to process 12 images per second. So you have a capacity issue. In your initial presentation, you have a goal of 12 images per second.
Yes.
And the output slides, you had 7.
7 per GPU. So if you use 2 GPUs, then it's more.
I have a question as well. You mentioned that you use motor engineers to validate the AI.
Mm-hmm.
How does that work with people who are not data science literature, how are you bringing them into the equation? You mentioned you have a mode of mechanic validating the AI. How does that?
Yeah, it's actually very interesting. Sometimes when you work in a co-working space in London, and you yeah. Well, I mean, we hired water engineers, and we have regular sessions. So when we sit together, we research sit together with them, and like, oh, we found these cases which are questionable. Can you explain like why is it like that? And we learn all these things that sometimes a panel might look perfectly fine to my eye, and maybe also has like little visual cues, only very subtle visual cues being somewhat different. But then you have to look at like, oh, the gap between this front left wing and the door behind it is in the middle a little bit smaller than on the outer part. It's like a very small signal, but it tells you that the wing has been pushed into the door. And those are things that I don't know how I would learn them just by looking at that workflow. But they just explain it so. So that's why, yeah. And there are multiple problems like that where we need experts for. So just for example, another very annoying problem that we have is just to even know which parts on different cars are the same physical thing. Because when we get it, we just get a bunch of images and a lot of like line data, which has like, oh, blah 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 repair. But then blah 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 is something different on a BMW than on a Mercedes. So we have to match that together to something which is visually the same meaning. And that's also something which there's a lot of work. So very good. Then we also work together with our data scientists and looking more into metadata. And that was a very important step.
Excellent.